In this video, we're going to take a look at how to use the mole to figure out the number of particles and the mass of samples of chemicals that we deal with in the lab. So you can think of the mole almost like a dozen for the chemists. A dozen contains 12 of something, and so a mole contains a certain number of something as well. Uh, Now, when it comes to molecules, atoms, and various particles, they're very, very small, and they come in a large quantity. So large that we came up with a special counting unit as chemists, and we call that special counting unit the mole. And so, one of the main scientists involved in defining the mole is Avogadro. And Avogadro found that if you have 6.02, this is a big number here, 6.02 times 10 to the power of 23 atoms of a certain element, then that many atoms of that element would have a mass that's equal to the atomic mass in the periodic table, but in grams instead of atomic mass units, instead of the AMU that we were used to seeing for one atom specifically. So if you have a mole of atoms of a particular element, you can find what a mass of that mole is by looking at a periodic table and looking at the mass there. That number, this 6.02 times 10 to the power of 23, is called Avogadro's number, again, based off the scientist that did a lot of work to determining it. So Avogadro's number. And so Avogadro's number, again, is 6.02 times 10 to the power of 23. That's a constant. You need to remember that. And that's particles per mole. Particles can refer to ions if you're studying ions, atoms if you're studying atoms, molecules if you're studying molecules, and then formula units if you're studying ionic compounds. So the big idea really from this is that 1 mole of anything really contains 6.02 times 10 to the power of 23 particles of that substance. So if you have 1 mole of iron, solid iron, that contains 6.02 times 10 to the power of 23 atoms of iron. If you have 1 mole of H2O, that contains 6.02 times 10 to the power of 23 molecules of water, because molecular compounds are molecules. And if you have 1 mole of NaCl, that contains 6.02 times 10 to the power of 23. We say for ionic compounds, not molecules, but formula units. Like that. So that is what a mole is. And let's just go take a look at a visual example of that. So here we can see we have the examples of items that are often grouped that we see in everyday life. So for example, we have 12 is a dozen, a ream is 500, and we get it in groups. So if I wanted 2 reams, I would have 1,000 sheets. If I want 2 dozens of donuts, I'd have 24 donuts. So we don't say, I'm going to order 24 donuts. Rather, I say I'm going to order 2 dozen donuts, and we know that that's 24. So just like with that, in chemistry, we would talk about the mole specifically. I'm not going to say I have 6.02 times 10 to the power of 23 atoms. I'm going to say I have a mole of that number of atoms. And if I have a mole of those atoms on a periodic table, then if a mole of those atoms, so let's say I had a mole of silver, would have a mass of 107.9 grams. One would be 107.9 AMU, but a mole of it's 107.9 grams. If I had 1 carbon, that would be 12.01 AMU, atomic mass units. But if I had a mole of carbon, it would be 6.02 times 10 to the power of 23. And then same thing with sulfur and all the other elements that are there. So as I mentioned, the Avogadro's number is 6.02 times 10 to the power of 23. We represent it with this symbol over here, uppercase N and then an A, that's a subscript there. And the units are particles per mole, where particles can be either the ions, the atoms, the molecules, or the formula units. And so here we can see that that's the big idea, that 1 mole is this many particles. And particles, if you look here, when you have a molecular compound like water, it's a molecule. When you just have a pure metal, for example, where you're dealing with just atoms straight up, it doesn't have to be pure metal only, but here's an example. It's just, that would be particles here, the atoms. If you had like salt, you're looking at the individual formula unit rather than the molecule. And so over here we can see moles of various substances. And so you can see a mole of carbon, a mole of sulfur, a mole of iron, a mole of copper, and a mole of mercury. And notice they don't seem to take up a lot of room. A mole is a big number. If you had a mole of something bigger, like a mole of peas, that takes up a lot more room. So if you click on this little tutorial here, you can see how much room a mole of peas takes up, and it's a lot. So why is it that a mole of sulfur um, only takes up a little bit of space on a plate, but a mole of peas takes up many, many, many planets covered in peas? Well, hopefully you're understanding that atoms are very, very small. So even though we have a mole of sulfur, atoms are so small they won't take up a lot of room. Their mass is very small. Their mass is very low. They're very small in size. Whereas peas, they are very, very large. It's kind of like saying, what takes up more room, a mole of peas or a mole of elephants? Elephants are bigger, so a mole of elephants will take up more space than a mole of peas, for example. And then we can go and we can take a look at just a little analogy for um, unit conversions. So we've already seen this, but you can write what's called a conversion factor. So let's say I have this problem here where I have a dozen, I want to know how many dozens of eggs are there in a box of 432 eggs. So I want to go from eggs to dozens of eggs. And so I can write a conversion factor. I can say that in 1 dozen, there are 12 eggs. So if I have 432 eggs, I can multiply by the conversion factor to figure out how many dozens I have. So I can use this conversion factor here, but I'm going to write it with the eggs at the bottom because I want to get rid of the eggs unit and the dozen on top. So I cross out eggs, and I get 432 times 1 divided by 12. Whoops, 432 times 1 divided by 12. I get 36 dozens is what remains there, dozens of eggs. And so the calculations we're going to be doing with moles are going to be essentially the same as the calculations that we just saw there. Just that this time we're dealing with moles rather than dozens. So the main formula we're going to start with is to find the number of particles, like the number of molecules, the number of atoms, the number of ions, or whatever you're dealing with, and the number of formula units. To find the number of particles, we use this formula here, where n, big N is the number of particles, is equal to little n. Little n is the number of moles. You can write MOL instead of MOLE. Times Avogadro's number, which is always 6.02 times 10 to the power of 23 particles per mole, and you can change what that particle is depending on what you're studying. So from this formula, we can derive other formulas. So you can actually get this other formula over here. For example, for this formula, we are trying to find the number of particles. For this formula here, though, we're trying to find the number of moles from the number of particles. So I'm just going to show you how to rearrange formulas to find the second formula here. So there's two main formulas. You can remember the first one as being n is equal to little n times Avogadro's number. That's your first formula. And if you want to find formula number 2, so formula number 2 is this, n is equal to big N over NA. I'm going to show you the derivation, how we figure that out. So what we do is we look at the first formula, n is equal to n times NA. And you look at the variable you want alone, you want to isolate that you're looking for. It's a little n over here. And so right now you'll notice it is multiplied by Avogadro's number. And so what I'm going to do is I'm going to unmultiply it by Avogadro's number. What's the opposite of dividing? Well, it's of multiplying, it's division. So I'm going to divide it by NA, and I have to do the same thing on the other side to keep everything nice and fair, to keep everything equal. And so the side that I've divided by NA that already had NA on the top, NA cancels out there, and I'm left with N alone. So I get N is equal to N over NA. So moles is equal to number of particles divided by your Avogadro's number. You could also, rather than memorizing formulas, just use conversion factors. But in reality, it's the same thing at the end of the day. So the conversion factors that are related to these formulas are 1 mole. In 1 mole, you have 6.02 times 10 to the power of 23 particles. Or you could say you have 6.02 times 10 to the power of 23. This should be particles here. I ran out of room there. Particles per 1 mole. In 1 mole. And you can use whichever one will lead to the proper unit cancellation in the question. So let's do a practice problem together over here. We have a sample of 1.25 moles of nitrogen dioxide, NO2. And so we'll do A together first. We want to find how many molecules are there in the sample. So for A, we want to do the number of molecules is equal to the number of moles times Na. That's what I'm doing there. I want to use this formula. So how did I figure that out? What I usually do is I write down my given information. So my given information, given, is going to be that I have, let's do colon there, colon. Erase that, do a colon. N is equal to 1.25 moles. And my Na, that you already know, is 6.02 times 10 to the power of 23. And in this case, particles will be molecules because it's NO2, molecules of NO2. You can say NO2 molecules, okay? So you could have just switched that around, but same thing. So that's my given information. And what am I looking for? So what is my unknown? My unknown is the number of particles, the number of molecules. And so I can continue that here. So that's my unknown. My next step is to write down an equation. So I put E for equation. And so to find that equation, I do N is equal to N times Na. That's my equation. And my last step is really to solve and find the solution. So substitute and solve are my S's. This method that I just used, if you look carefully, it spells out guess. So substitute and solve, basically I'm plugging in the numbers that fit into this equation from my question. And then, so that's substituting, and then solving is coming up with my final answer. And then there's usually another part to the guess. It's a S, a third S, and that would be our statement. But we'll do that after. So our N is going to be equal to, and we put all our units in. We do number of moles is 1.25 moles. And we're going to multiply that by Avogadro's number, which is, I'm going to put it in brackets here, 6.02 times 10 to the power 23 NO2 molecules per mole. And so what I forgot to do there is I forgot to put the unit here as molecules per mole, because that's the unit. And you'll notice that we have the right formula because everything will cancel out. This is the proper conversion factor. When we are trying to go from the number of particles or number of moles to number of particles, n to little n to big N, this is the conversion factor we want to use because it cancels out our moles like that, and you're left with particles or molecules left. So we can go ahead and plug that in our calculator. Make sure you look at the tutorial for how to plug in scientific notation in your calculator. But I get 6.02 times 10 to the power of 23, and I multiply that by 1.25. Now, I get this, so continue over here. I get N is equal to 7.525 times 10 to the power of 23. It's a 23 there. NO2 molecules. Now, you do need to make sure you're following your significant figure rules. So in our question, the smallest number of significant figures, that's what we go with, is 3. 3 significant figures. So for my third S that I have in my guess method, I'm going to do that. I'm going to say, therefore, the number of particles, n, is approximately equal to, rounded to the correct number of sig figs, 7.52, because this here is 2, look next door, stays even, 52, times 10 to the power of 23 NO2 molecules. And so this method that we did here is called the guess method. And so what we did there is we had our given information from the question, what was given to us. We wrote down what our unknown is, what we're looking for, which is basically our number of particles, number of molecules. We wrote down an equation, E. We then decided to substitute, so I put in all the numbers into the equation. And then finally we decided to solve by finding our final answer and plugging everything into our calculator, and then we wrote a statement. And we made sure that everything followed our 3 significant digits in that case, because that was the smallest number of significant digits there. And what you notice is that we used our conversion factor, which is 6.02 times 10 to the power 23 NO2 molecules per mole. And so when you're doing a question like this, what you want to do is you want to make sure that you include all your units and show all your unit cancellation. And you also want to make sure that it's nice and neat and easy to follow. This is not the greatest model because I didn't have a lot of space. I would leave you more space on a test or a quiz. And you want to make it nice and linear and easier to follow as well. And don't forget your therefore statement. These 3 dots here, that means therefore. Therefore, number of particles is approximately equal to 7.52 times 10 to the power of 23 NO2 molecules. So what I'm going to do now is I'm going to do part B. We want to figure out how many atoms there are in this sample. So this is a bit of an extension. This is a bit of an extension here. So we'll do part B over here. So let's write a conversion factor out. In one NO2 molecule, there are 3 atoms. In one molecule, there are 3 atoms, okay? Because there's 1 N and 2 O's, and that's in one molecule, okay? Now, we don't have one molecule. We have this many molecules. So think about it this way. If you had 2 molecules, you'd have 6 atoms. You'd multiply that by 2. So let's use a conversion factor to figure out how many atoms we have total in the sample. So if I want to find total number of atoms, I would say that that's going to be equal to my 7.52 times 10 to the power of 23. Now let me be clear about something here. I would actually use the unrounded answer in this question. I would actually keep it in my calculator. So I would write down my 7.52 times 10 to the power of 23, but I'm keeping the unrounded answer in my calculator. You don't want to round in every single question. So I'm keeping my unrounded answer in the calculator, my 7.525 times 10 to the power of 23. That's what I'm using in my calculator. So NO2 molecules multiplied by the conversion factor, but make sure you write it the right way. I want to cross out molecules. So I'm going to do times 3 atoms for every 1 NO2 molecule. And so I can cross NO2 molecules out, and I'm left with atoms. So when I do that, I get my answer from the previous question times 3. I get 2.2575 times 10 to the power 24 atoms. So I wrote a conversion factor first. That was my first step. Next step is I wrote down what I was looking for, and I did my my processes. And then I'm just going to write a little therefore statement in my third step here. My third step, I'm going to say, therefore, the total number of atoms is approximately, and I'm going to do this the correct number of sig figs, the 3 sig figs, right? Because there's 3 sig figs in my question. So I look next door here, it's going to round up. So it's about 2.26 times 10 to the power of 24 atoms. And so that there would be my final answer in the therefore statement to the proper number of sig figs, which is what's in the original question here. Don't count the Avogadro's number as part of your sig figs. Don't count stuff from the periodic table as part of your sig figs. Count really what's given in the question as part of your sig figs in determining that. And then here, I wouldn't count the 3 atoms here because that there is an exact number and it wasn't really given in the question. So it's an exact number. There's exactly 3 in there, so it's an infinite number of sig figs, so you wouldn't count that. So really we're focusing on 3 sig figs there, and this is our final answer over here. That was for the total number of atoms. What would you have done if I asked for only nitrogen atoms? So think about it, try it out, try to do a conversion factor. But basically, if you only ask for nitrogen atoms, I'd probably just do the number of molecules of NO2 times 1, because there's only 1 nitrogen. And if you only ask for oxygen atoms, I'd probably do the number of NO2 molecules times 2, because there's 2 oxygen atoms. So think about it that way when you're doing these problems. In the next video, we're going to try to solve problems 2 to 5. And then afterwards, we're going to go to the next section, which is molar mass, moles, and mass.